Hey YouTube, welcome back to my data structures in Typescript series. In this video, we're going to go over the implementation for a linked list. So let's start off with a linked list node. The linked list node is a very simple definition. We have a value, which is type T generic, and then we have a next and previous value. This is a doubly linked list. And the next value can be a linked list node or null, and same thing with previous. And when we construct this, we just set the values, and then we set the pointers next and previous to null. So then here in the linked list, we have a private variable called list, which is a list interfaced or undefined. The reason why we set up the types like this, where we have the types of head, tail, and size in this list type, is because it's better for TypeScript type inference for the undefined or nullability type to be outside of this type, because we get better type inference. There's a few things that don't work if we do something like directly like this, where we have private head linked list node or undefined. And that's because when we go in to implement this linked list in our methods, when we do null checks, we want to if head is not undefined, then we know that tail is not undefined as well. So just setting this type to be like this is better for type inference. So when we construct it, we just set this dot list equals undefined, and let's hop into these methods. So I have these methods. I like to create my data structures and separate the methods according to their concerns. So the first few methods, what am I doing? Okay. The first few methods I have are some methods called niceties, I like to call them. So these are your size and is empty helpers. So the size is just going to return if this dot list is defined, then we'll return this dot list dot size. And we know we have a size because it's right there, which we will increment manually every time we add to our linked list. Otherwise, we will return 0. So that's the size method. Is empty is pretty simple as well. This just returns if this dot list is defined or not, because we have a list or undefined. So if it's defined, then we know we have elements in our linked list, and of course it can't be empty. Here I have insertion. I label these as insertion. So the first method we're going to implement is the add front method, and what we're going to do first is create the new node. So we're going to do new node equals a new linked list node and pass in the value. And then there's two cases for the front. If the list is defined and if it's not. If the list is not defined, we're just going to treat it, and we're just going to do head is new node, tail is new node, and size is 1. If there is a list, that means we have to link the previous head backwards, because this is a doubly linked list. So what we're going to do is we're going to set this dot list dot head dot previous equals new node. We're going to link it backwards, and then we're going to link it forwards with the new node dot next equals this dot list dot head. Then we're going to update the head pointer of our list to reference our new node, like that. And then we're going to increment the size by 1, and that's it. Whoops, this dot list dot size. So there's two cases when adding to the front. If there's already a head existing, we have to do the pointer manipulation. Otherwise, we just initialize it. And the same thing is similar for the back. We're going to create a new node equals a new linked list node, and we're going to pass in the value. And then if this dot list exists, we're going to have to do the pointer manipulation. Otherwise, we're just going to create the list right here with the head as the new node. Same thing for the tail, and the size is 1. Otherwise, we link the old tail forwards. So we say this dot list dot tail dot next equals new node. Then we link the new node backwards. New node dot previous equals this dot list dot tail. Then we update the tail pointer. So this is going to be this dot list dot tail equals new node. and then we just increment the size. Whoops, I keep saying this dot size, this dot list dot size, and there we go. So addat is going to be a method where it's going to take in two parameters, the index to add and then the value. And this one's going to be a bit more trickier than the adding front to add to the back, because we potentially have to walk through the array. So if the index is 0, that means we want to just add to the front. So we're going to call this dot add front, pass in the value, and then just return out of this method. If the index is this dot size, that means we want to insert at the end of the linked list. So we're just going to do this dot add back and value, and then return. And then otherwise, that means the person, the consumer of this linked list, wants to insert in the middle. So we have to make sure that the index is not out of bounds. So we check right now to see that. So if I is less than 0, or I is greater than or equal to this dot size, or this dot list is not defined, then we'll throw new error, and then I have this out of bounds error that I defined up there. Otherwise, we can traverse to I-1 and then do our pointer manipulation. So I'm going to set a current pointer to this dot list dot head, and then I'm going to traverse to the index. So I'm going to do for loop. So I'm going to do a for loop, and I'm going to traverse until j is less than, as long as j is less than I-1, then I'm okay with looping. And then I'm going to set cur equals current dot next. And then I have to tell Typescript here that this is never going to be null, because we've already checked to make sure that the indexes won't go to the last element, which is a null element. Yeah. So after this for loop, the variable current will be pointing to the node before the node that we want to, before the spot we want to insert at, because we want to insert at the I index, and we loop I-1 times. So then we just create the new node right here, linked list node, pass in the value, and then we want to link the previous node. So the previous node right now is current, and we set the current.next, and we tell Typescript that's not null with the assertion, the non-null assertion, and we set the previous. So then we want to link the node that will come after our new node. We want to link that backwards. So we set cur.next, and we tell Typescript that this is not null. So the cur.next.previous equals new node. And then we set new node.next equals current.next. And we tell Typescript that's not null. And then once we link backwards, we have to link forwards. So we want to do new node.previous is equal to the current one, and then cur.next equals new node, and then we'll increment the size, and that is dot list again. So yeah, that's the addat method. We check to see if the index is at the start or front or back. If so, we're just going to call add front, add back, and return. Otherwise, we want to traverse to the node that comes before where we want to insert. But before that, we want to make sure the index is inbound and not out of bounds, and then we can do our traversing. Then we create our node, and then we do some pointer manipulation on the node after that comes after our new node, and the one before, and then increment the size. Peek front and peek back are simple to implement. I call these accessing methods, and these are easy because we hold references to the head and tail. So if the list is not defined, we're going to throw some sort of error, and I created the empty error. Of course, there's police, and if it is defined, we would just return simply this .list.head. And the same thing, why is this? Oh, this list.head.value. And the same thing for peek back, except we return the tails value. The next set of methods I call searching, because we have to search. And actually, before I go into searching, quickly I'll just go to the times. Peek front and peek back are constant because we're just returning that. And addat is O of n, because we potentially have to, in the worst case, do this traversal, even if we are at the best case, getting constant time by inserting at the front and back. And then front and back insertion are constant because we're just doing pointer manipulation at the front and back, and these niceties are constant. So going back to the searching, which all of them take O of n because we potentially have to do a linear amount of work, get is quite simple. If the index is out of bounds, or this.list is undefined, then we'll throw a new error saying out of bounds error. Otherwise, we want to traverse to the element with the ith index. So we will say let j equal 0, and then we will want to iterate I times. So while j is less than I, we need to have a pointer pointing at the head, and then we just simply traverse cur equals cur.next. And we get this error because this should actually be checking to see if it's undefined. And then we want to tell Typescript that there's no way of current being null because we done the index checks, and then after we increment j as well. Then we simply just return cur.value because current will be pointing at the ith node in the linked list. So the index of function up next is going to take a linear amount of work as well. And what this function does is it takes in a value t and a potential optional equal function and returns the index of the element that has a value of t if it is found. Otherwise, it's going to return -1 if it's not in the linked list. So the first thing we can do is a check to see if the linked list is even defined. So if it's not defined, then we're going to return -1. The thing we need is to have an equals function to be the check. We want to loop through the linked list and call this function on each element to see if it matches the value. We take in an optional equals function because the elements of the linked list are potentially complex objects that might not have primitive comparison functions. So we set the equals function equal to the equals function if it's defined, or our default equals. And to show you what the definition of the default equals function is, there's another file called utils, and I just have a generic default equals which takes in two a and b parameters and just returns the JavaScript triple equals a equals b. But if it is equals function is defined, then we're going to supply that. So then this is kind of like clockwork. We have a index and then we have a pointer to the node, this.list.head. And then we're going to say while the current value does not equal the target value that we're looking for. So while equals function, and then we pass in cur.value and then value. While this is not true, we want to keep looking forwards, right? So what we do is we set cur equals cur.next, and then we want to increment I, and we have to tell Typescript again that this is not null. If someone knows a better way of doing this, to tell Typescript that there's no way this is null, then I guess there is a way for it to be null in this case, but in the previous cases we were doing index checks. But if someone knows a better way to do this, because technically non-null assertions aren't the best, because my linter is also telling me that, then comment down below. But I don't think anyone's going to comment down since I don't have any viewers, because I'm a loner. Anyways, I'm getting off track. We want to increment the index because we want to eventually return this. Then when this expression of value is to false, that means these two do equal, and then I will be set the correct index. So all we're going to do is return I, and that's index of. Contains is something similar. What it does is it returns a boolean whether or not an element with the value t is in the array or not. Not arrays, right? Linked list. And this function is very easy. Not this function, this method. It's very easy. There's 2 lines. What we do is we get the index of the element with t, and if it's -1, we just return if the value is -1 or not to check if the element is in the array. Sorry, not array, linked list. It's getting late. Okay, so const index equals this dot index of, and we're going to pass in the value, and then if the equals function is defined in this method, we'll pass it, and we're using a ternary operator. Otherwise, we're going to pass undefined. Great. And then what we return is if the index does not equal -1. So if it does not equal -1, that means we have an index in the linked list, and that means our linked list contains it. If it is -1, then we return false, because that means the linked list does not contain the element. And of course, this should be O of n as well. So remove front and remove back. Just remove the front and back, and they're both constant amount of time because it's just pointer manipulation. First, we check to see if the list is undefined. If it is, then we're going to throw a new error with empty error. Otherwise, these two methods return the value of the removed value. So we're going to first save the value by setting the value equals this.list.head. And then what we're going to do is we're going to check to see if this.list.head, if there is a next element in the linked list. Because if there's not, that means only the head was, the linked list was only one element, which was the head and tail itself. So what we'll do is just set this.list equals undefined, right? If it is defined, then we have to set this linked list, this node's previous pointer to nothing, because this will be the new head, and then we'll have to move the head pointer forward. So we set this.list.head.next. So this is the new head. We set the previous of that node to null, and then we move this.list.head forwards to this.list.head.next. And then remember to always keep the invariant of the size correct. And then at the end, we're going to return the value because that's the signature, and this.list.head.value. Similarly, for the remove back, it's a constant time operation that returns the value of the removed value. What we do is if the list is undefined, we're going to also throw an empty error. Otherwise, save the value as this.list.tail. If the tail is defined, we're going to have to do some pointer manipulation. I'm going to skip that for now. Otherwise, we're going to set this.list to be undefined because we're just deleting the entire list. So then what we do is we set this.list.tail.previous.next now. I'm going to switch the order, equal null. And then we set this.tail equals this.list.tail.previous. And we're getting type errors object is possibly null. Oh, and that's because I have to set the previous, right? Yeah, so if there's a second last element, then let's do the pointer manipulation. Otherwise, just set it undefined. And we don't have to change the size, decrement the size down by 1, because we're just totally deleting the entire object of this.list. Then at the end, return the value. So remove is quite simple because it's going to use removeat and index. Basically what it does is it takes a value t and it removes the element that has the first element that in the linked list that has a value t. So what it first does is it does this const index equals this.index of value, and then if the index is -1, that means it's not in our list. So I think it would actually make more sense to return a false value instead of throw, but I'm just going to throw now. I might change that in the source code later on. So we're going to throw a new error saying value does not exist error. Otherwise, we're going to return this.removeat index, and the removeat we're going to implement right now. So remove is pretty simple. It just uses the two methods that we defined, index of and removeat. So removeat is quite similar to addat. We just have to traverse to the specific element that we need to do and then do the pointer manipulation. So because of that, that's going to be O of n, and its parameters, it takes in an index, which is a number, and so we can traverse to that, and then it returns the value of the removed node. So first we check to see if the index is the head. If so, we're going to just call this dot remove head, and then we're going to return, not remove head, remove front. And then we're going to return, the value of this dot remove front because it also returns the value. If the index is this dot size -1, so the index is inclusive such that like we don't actually use this dot size, we use this dot size -1 for the tail, then we're gonna return this dot remove tail. Whoops, remove back. If not, that means the person wants to delete something in the middle of the linked list. So first we want to make sure that the index is in bounds, is not out of bounds. So we make sure if I is less than 0, or I is greater than or equal to this dot size, or this dot list is undefined, then we're going to throw a new error saying empty list, empty error. So if that if statement does not catch, that means we're free to traverse. So let j equal 0, then let cur equal this dot list dot head. And what we want to do is we want to traverse I times. We want to actually land, we want cur to land on the node that we're going to delete. So we just set cur equals cur.next and j plus equals 1, and then that non-null assertion. After, cur is going to be pointing to the node that we want to delete. So what we do is first let's select the previous pointer. So cur.next.previous equals cur.previous. And then cur.previous.next equals current.next. So we're just rearranging the pointers like we did in the previous video. Then we're going to decommit the size, and then we're going to this .list.size. I always mess that up. And then we're going to return the value that we have saved. Oh, we have not saved it. So I want to save the value right here, I guess. So I say const, oh, whoops, no, right here. Const value equals cur.value. Actually, we don't even have to save it because current's still going to be pointing to the delete value. So we can just return current.value right here, and this will still work. So that's removeat, and that's the last not last method for the deletion methods. The last one is clear, and that's very simple. We're just going to set this .list to undefined, and that's going to be a constant time operation. The final two methods are JavaScript specific utility methods. One is if someone wants to create or wants to append values to the linked list from an array, then we're going to do that. It's going to be from array, and it's going to return the value of the linked list. I actually included this when I was thinking of implementing the builder pattern, but because I think I removed it up above in the other methods, so I'm not going to return the linked list, but I'll just do that for this video right now. So you can just ignore that if you don't understand what the builder pattern is. So what you want to do is you want to loop through the array. So for every element A of the array A, we're going to do this dot add back A. Pretty simple. And then we'll just return this. Here, this is a generator function that returns an iterator. And what this does is if a object has a method that has the specific name symbol.iterator and returns an iterator, then the object is iterable itself. And what the iterator protocol in JavaScript does is this method needs to return values that have a done, which is a Boolean. So this could be like true or false, and it has a value, which is the actual value. So you can do that manually with creating an iterator, or you can use a generator which uses the yield keyword, which is pretty simple. So if this .list is undefined, then we're just going to return. Otherwise, we're going to initialize the current variable, and this is going to be a linked list node typed with a T generic, or it's going to be null. And then what we're going to do is we're going to loop through. So we're going to set cur equals this list head, and we're going to loop through as long as cur does not equal null. and then we'll set cur equals cur.next for the increment step of the for loop. And why is this? Okay, I'm just gonna ignore that for now. And then we'll just do yield cur.value. And the reason why we get these is because this is not linked to this node. And yeah, so that was it. The linked list had a bunch of methods to implement. We had some niceties, we have insertion, we have accessing, we have searching, deletion, and helpers. The stack and queue, on the other hand, are very easy to implement. They leverage the linked list heavily. And yeah, this is just like one of the data structures that requires a lot of methods because it's one of the foundational data structures that we build up upon with the stack and queue. So thanks for sticking with me. I hope you've learned what a linked list is and how to implement it. And I'll see you in the next video where we'll probably talk about arrays versus linked lists. See you then.